We're now going to introduce the concept of a derivative. And to do that, we're going to first go back to the slope of a line tangent to a curve. Recall that when we talked about the secant line, that was the average rate of change. The tangent line, however, was the instantaneous rate of change. One of the ways we talked about the slope of a secant line was s1 minus s0 divided by t1 minus t0. We can also talk about this another way. I can say that the average velocity is st minus sa divided by t minus a. And that's the average velocity over the time interval bracket a, t, end bracket. And now that we know about limits, I can talk about the instantaneous velocity being equal to the limit as t approaches a, that is, as t gets right on top of a, of s of t minus s of a divided by t minus a. Let's give the example of that apple being thrown up in the air. If we neglect air resistance, that distance formula, the distance above the ground of the apple, is s of t equals negative 16t squared plus 96t. And let's look at what happens at the point p1, 80. To find the instantaneous velocity, I take the limit as t approaches 1 of s of t minus s of 1 divided by t minus 1. Plugging in the values for s of t and a equaling 1, this is what I get. And I know I can't plug t equals 1 into my denominator, so I'm really hopeful I'll be able to factor this. And that way the t minus 1 will divide out with a t minus 1 in my numerator. Let's see if I can get that to work. I first pull out that negative 16, and now I'll go ahead and continue to factor. And when I do that, I find out I can divide out that t minus 1, leaving me with the following. Using my limit laws, I can pull out that negative 16, and because t minus 5 is a polynomial, I can just do direct substitution. And when I do that, I find that the instantaneous velocity at time t equals 1 is 64. The instantaneous velocity is also equal to the slope of the tangent line. The next question I'm going to ask is to give me the equation of that tangent line. To find the equation of the tangent line, I have a point and I have a slope, so I'm going to use the point-slope form of a linear equation. I'm going to go ahead and plug in my p and my m, and now I'll go ahead and put this in slope-intercept form, and there is my equation. Let's see if this looks right when I graph it. There's my equation, along with a point 1, 80, and now let's graph that tangent line. And sure enough, that line is in fact tangent to my curve at the point. And here's a summary of what I just said. The slope of the secant line is fx minus fa over x minus a. That's on the interval a, x. And the slope of the tangent line, or the instantaneous rate of change at that point a, is the limit as x approaches a of f of x minus f of a over x minus a. Let's do another example. Let's find the equation of the line tangent to the graph of f of x equals 3 over x at the point x equals 2. First, let's set this up. Here's the problem set up. And now let's go ahead and plug in x and 2 into our function. And we right now have complex fractions. To get rid of the complex fraction, one way to do so is multiply the numerator and denominator by the lowest common denominator. In this case, that's 2x. We get this. And then finally, I get this. Now, I want to be able to divide out that x minus 2. So if I look at my numerator, I see an x minus 2 hiding in there. And if I pull out a negative 3, I get a x minus 2 in the numerator and an x minus 2 in the denominator. Now I can use my rational function rule to just do substitution, and I get that the limit as x approaches 2 is simply negative 3/4. The question is asking for the equation of the line tangent to the graph at that point. So first I'll need to put it in point-slope form. Now in this case, I didn't give you a point. I merely said at x equals 2. So I'm going to have to figure out if x is equal to 2, that means that f of x, or y, that's equal to 3/2. And multiplying this out, I end up with the following. And this is the final answer. That is the equation of the line tangent to the graph of 3 over x at x equals 2. Another way of defining the rate of change in slope of the tangent line is looking at, instead of the difference of x and a, looking at a plus h and a. That is, we're having a small change h. So the slope of the secant line is equal to f of a plus h minus f of a divided by, and the denominator ends up just being h. That's because I would have a plus h minus a, which is equal to 8. The slope of the tangent line is that same slope, But now we're taking the limit as h, that change between a and a plus h, as that change goes to 0. Let's do a quick example of this. I want the equation of the line tangent to f of x equals x cubed plus 4x at the point 1, 5. Let's go ahead and set up my formula for the slope of the tangent line. After I plug in a plus h, allowing a to be equal to the number 1, since I'm looking at the point 1, 5, I get this. When I multiply out 1 plus h all cubed, and off to the side you can see my work for that. I first multiplied 1 plus h times 1 plus h, then I took that answer and multiplied it by 1 plus h again. Now let's go ahead and plug that in. I just realized I had 1 cubed minus 4 times 1 instead of plus. I've gone ahead and fixed that, and I've multiplied this all out, and we end up with this. Again, I can't just let h equal 0, but it looks like I can factor out an h in my numerator. And when I do that, I get it down to this, and since this is a polynomial, I can do direct substitution into my limit, and then I get my slope being 7. To find the slope of the tangent line, I just use that point slope formula, and I get the equation of the line tangent to f of x equals x cubed plus 4x at the point 1, 5 to be y equals 7x minus 2. So this leads us to the definition of the derivative. That is, f prime of a, the derivative of f at a, is equal to the limit as x approaches a of f of x minus f of a divided by x minus a, or the limit as h approaches 0 of f of a plus h minus f of a divided by h. On an exam, when you're asked to find the derivative by definition, you have to use one of these formats. Even if you know shortcut methods to do derivatives, you will get no credit on exams if, when asked to find the derivative by the definition, that means you have to use this formula. So a derivative is nothing more than the rate of change or the slope of the tangent line. Let's do one final example. If we're given f of x equals the square root of 2x plus 1, and I'm told to find f prime of 2, specifically by the definition of the derivative, I need to choose one of these two definitions of the derivative. I'm going to use the first one. That is, f prime of 2 equals the limit as x approaches 2 of f of x minus f of 2 divided by x minus 2. Plugging in values for f of x and f of 2, I get it down to there, and finally, I get it down to this form. Unfortunately, there's nothing I can do to my numerator that would factor to get me an x minus 2, at least not something easy. So what I'm going to do is multiply by the conjugate of square root of 2x minus 2. The conjugate of square root of 2x minus 2 is square root of 2x plus 2. When I multiply out the numerator, I get 2x minus 4. I leave the denominator alone because I see if I factor a 2 out of my numerator, I can divide out that x minus 2, because again, this is a rational function. I get this down to a slope of 1/2. I said slope, I was looking for the derivative. Those are the exact same thing. And there's our introduction to the derivative.